now I'm going to look at the theory behind paired sample t-tests. So I want to show you why I want to carry out a paired sample t-test. So why should we use them? Now, the reason that you need to look at a paired sample is because of sampling error. So the amount of variation between subjects, between the experimental units you're using in the experiment, can be high, and it can be larger than the amount of variation you're going to get in the treatment. So if that's true, the only thing you're going to see when you compare the means before and the means afterwards is that the variation in means in the control exceeds that of between the control and the treated group. So in this case, that's not going to be very useful. We need to define if there's a response by removing some of that variation. So we can do it by blocking. We do this to deal with confounding and problems with experimental design. The best possible way of doing it is pairing, which means you get the same person before and after. So you put them both in the control and the treated group. Now you can do a crossover study where you split your experimental units into two halves. So one half of them have the control first and then the treatment. One half have the treatment first and then go to the control. And that should remove any effects to do with temporal effects of time in the study. Blocking, if you do it properly, can remove almost all the unwanted variation, but the cost of it is you need to take in more experimental units to match people together. The problem with pairing is they're not independent, so that reduces your numbers of degrees of freedom and reduces the number of data points that you have. You're usually going to measure the outcome variable before and after a treatment, so they're acting as a control and reference, and then you look at a difference in means. So the criteria for using a t-test is you've got to have one treatment variable, two samples which are matched, so therefore they're going to be automatically the same size. The variances have to be similar, and in theory you would apply the z-test if there were over 30 pairs and the t-test is less than 30 pairs, but in practice we only ever apply the t-test. If the two samples are from the same population, you'd expect the difference in means to be close to zero. So that means the treatment, if the treatment is having no effect, so it's not changing the population at all, then the mean difference will be zero. You find the distance between the before and after in terms of as a ratio of the standard errors between the means. So you calculate the difference d for each pair of observations, calculate the mean difference and the variance of the difference. Remember that n is the number of pairs of observations, not the total number of observations, and the degrees of freedom will be n minus 1, and then you put it into this formula. So the standard error for the difference of the means is the square root of the variance, or the standard deviation squared of the difference, divided by n, the number of pairs you have, and the t statistic, the calculated t value for a paired t-test, is the mean difference divided by the standard error of the difference.